I was awarded, as I mentioned before, awarded second place for United States Inventor of the Year for this discovery, which was a big discovery. My colleagues won the Nobel Prize in Medicine for this discovery. So it's been getting a lot of attention. A lot of people are touting this as possibly the biggest medical breakthrough of all time, as soon as we can actually do something with it, okay, where we can actually give people a pill to treat their problems. But right now, this is very exciting in the scientific world. So let's go back to this bricklaying model. What's happening? How's telomerase doing this? Well, in a reproductive cell, that brick layer is still going to fall off at the end of the wall. But like an angel, telomerase comes in and replaces that brick. And as a result, the telomeres don't get shorter. And I want to get ahead of the game. We have shown that if we put more telomerase into the cells, the telomeres actually get longer, which is suggestive of a reversing aging. And that's how we're trying to approach this, is trying to overproduce telomerase in our cells to reverse aging. So there's two words that I've come up with that I mentioned today, telomerase and telomere. A lot of people get those mixed up. I just want, so you really make it clear. Telomerase is the enzyme that lengthens the telomere. So the telomere is the tip of your chromosome. Telomeres are the tip of your chromosomes. Telomerase is the enzyme that re-lengthens them. All right. What would happen if we were to put telomerase in all the cells of the body? And before I go further, I do have a question that I do have a book for. Anybody here who like I'm going to ask a question, but if you obviously know it because you've listened to a previous talk or something like that, you probably shouldn't answer. So if somebody who isn't here, who doesn't know the answer, how long do lobsters live? Anybody know how long a lobster lives? Okay, so now, since nobody answered the question, how about anybody who wants to answer it, answer it.
I had over 120 years, 120 years.
Anybody?
I don't know.
Huh?
I don't know. I don't know.
So that's the answer right now. They have undetectable aging. Yeah, so here's your book.
Well done.
Thank you. It's been known for a long time, or let's say for a long time, at least 150 years, it's been that people have been asking the question, how long do animals live? Before days of Darwin, nobody cared about that kind of stuff, but people after Darwin started collecting animals. Now the problem is that most animals don't have things like rings on a tree, so you can't count them to figure out how old they are. So the only way to figure out how old a lobster will live, or some other animal, is to catch them when they're born, put them in a cage or an aquarium, and watch them. Well, 150 years later, lobsters are showing no signs of aging. And it was published recently. Oops, too many clicks. Hold on. It was published that the reason why lobsters show no signs of aging is because they have telomerase produced in all their cells, not just the reproductive cells. They have it in every single cell of their body. Now, remember I also said that short telomeres increase your risk of cancer. What's also been published, this thing's starting to not work right. Okay. It's also been published now that lobsters rarely get cancer and other diseases. And it's all because of the fact their telomeres don't get short. They have telomerase produced in all their cells. They don't have telomere shortening. They show no signs of aging, and they rarely get diseases. This is a good thing. I want us to all be like these lobsters. Now, of course, lobsters do have a bunch of other ways to die. This doesn't make them immortal. They still get eaten by everybody who likes lobsters. But there's other animals, too, that have now been identified to fit in that same category. Tortoises, clams, humpback whales, fish, even some birds have been shown to have no detectable aging. Now, Charles Darwin had a pet tortoise named Harriet, and she just died recently at 180 years old. And by the way, when I gave this presentation yesterday, somebody in the audience raised their hand and said, I've met Harriet. I don't know if anybody here is. Apparently she was in a zoo here in New Zealand.
Yeah, an Australian zoo, I think.
An Australian zoo? Okay. So, but she died of a viral infection of some kind, not from aging. And there's also tortoises on this planet that are over 200 years old, documented to be over 200 years old, and they don't look like old tortoises. They're bigger, but they're still healthy. There was a whale found with a harpoon in it, and they carbon dated the harpoon and found out that the harpoon was 130 years old. So how old is that whale? I mean, it had to be big enough to throw a harpoon into when it was 130 years ago. So it's definitely older than that. Now, I'd mentioned that none of the animals have rings on a tree, like things like rings on a tree that you can count. The exception is clams. So people start realizing that the number of stripes, each stripe represents a year on those clams, if you look at the top right picture. So this is Ming the clam. She's called Ming because she was born in during the Ming Dynasty. And unfortunately, it doesn't say here, but she actually died while they were counting the bands, because they were trying to really count every band down into the hinge section of it, and actually killed the clam. But the scientists believe there are clams down there that are probably 2,000 years old, but they haven't seen them yet. So we really want to do this in humans, right? We want to get telomerase produced in all of our cells in a human. And we haven't done that yet. Otherwise, I wouldn't be standing here talking about curing aging. It'd be called aging cured. But people have now done this with mice. Scientists at Harvard University have engineered mice and made it so that when they got really old, they fed them a certain supplement that lengthened their telomeres, and as a result, they got younger. It's the first time in the history of the planet that anybody has successfully reversed aging in any life form. And the doctor was Dr. Rhonda Pennell. He was interviewed by Diane Sawyer on ABC News. I just want to show you the news clipping. It's about 2 minutes long.
And now, eternal youth. Is it in a cage around the corner? News tonight of a breakthrough for some pioneering mice. But we always wonder, what does a fountain of youth for rodents reveal for humans? Here's Sharon Alfonsi reporting.
I feel tremendous.
In the Moody Cocoon, it's a swimming pool that turns back the clock for a group of senior citizens. But now researchers have found a way not just to stop, but reverse the aging process. The key is something called a telomere. We all have them. They're the tips or caps of your chromosomes, seen here in yellow. This is what it looks like in a young adult. But as you grow older, the telomeres become damaged and frayed, and as they stop working, we start aging, experiencing things like hearing and memory loss. Scientists took mice who were prematurely aged, added an enzyme, and essentially turned their telomeres back on. You can see it before the enzyme, after.
Their brain function improved, their fertility was restored. It was a remarkable reversal of the aging process.
Look at this picture. The mouse on the right has bad skin, gray hair, and is balding. But the one on the left had its telomeres flipped back on.
And you could see that essentially you now have a dark coat color, that the hair is restored, that the coat has a nice healthy sheen to it.
Even more dramatic, the change in brain size. This is before. The mice had 75% of a normal brain, like a patient with severe Alzheimer's. But after the telomeres were reactivated, the brain returns to normal size. As for humans, while it is just one factor, scientists now say by looking at our blood cells and measuring those telomeres, you can get a better idea of how well you'll age. The longer the telomere, the better the chances for a more graceful aging. But as for tinkering with them and turning back our aging process, researchers say we still have a long way to go. Sharon Alfonsi, ABC News, New York.
Well, I think that's really exciting. I mean, as I said, it's the first time this has ever been really done, and it's been done by lengthening telomeres. That's the only change that was made in these mice. The mice got younger by simply lengthening the telomeres. And, you know, me and probably a lot of other people here probably have family members suffering from a lot of age-related diseases. My father and my younger brother are both suffering from severe Alzheimer's right now. And this is suggesting that maybe this might even cure Alzheimer's. The memory of these mice came back, suggesting that Alzheimer's isn't the loss of memory, but maybe just the loss of access to the memory. And so if we could figure out how to reconnect everything, the memories might come back. just by lengthening the telomeres. So I'm pretty excited. I'm really anxious to develop something that will actually be potent enough to lengthen telomeres and start testing it on people, especially people like my father and stuff. So we can't do this in humans, but not yet, all right? And because I think we're close. Now with the mice, they had to engineer the mice. They actually took a single cell of a mouse, engineered it so that they could flip the gene, the telomerase gene, on and off, and then they physically shortened the telomeres so that the mice would age prematurely. Then they allowed these mice to then they grew that single cell into an adult mouse, and then bred that mouse and made a colony of mice. Then they let these mice get really, really old, and they fed it that supplement that turned on the gene, and the mice got young again. Now, that supplement will not work in humans, and it won't even work in other mice. It only works in these mice, but it is the best support of concept that we've ever had, that lengthening telomeres in humans will actually make us younger, just like these mice did. So this is what my company is all about. My company is called Sierra Sciences. It's in Reno, Nevada. Everything we're doing is trying to figure out a way to produce telomerase in all of our cells to lengthen our telomeres. This is the strategy that we're using. I went one slide too fast here. Okay, so our strategy is to take into account that telomerase, just like every other protein in the human body, is made by a gene. Okay, so we have here, the gray bar is the chromosome. Remember, it's 100 million bases in length. Along this DNA is found genes. One of those genes is telomerase. The telomerase gene, the function of that is to produce telomerase inside the cell. Now, next to every gene, there's a regulatory element. It's like a light switch. It turns the gene on and off. In our reproductive cells, that gene is turned on. That switch is turned on. As a result, telomerase is being produced. But the reason why it's shut off in all the other cells of our body is because some protein binds to that regulatory element and shuts it off. And as a result, no telomerase is produced. That protein is called a repressor. So what my company is doing is we're looking for anything, chemicals, natural products, plants, anything, something shown in green that will bind to that repressor, dislodge it, and allow the gene to turn back on again. Fairly simple. It's just a lot of work. Okay, so that's what we're doing. We're looking for ways to turn it back on. Now, we have found things that do this. Some are very weak, some are a little bit stronger than that, some are a little bit stronger than that. So it's not quite like the regular light switch. Think of it like a dimmer switch. The dimmer switch now is being turned on and on and on. Well, we've learned now how to turn it on a little bit. Okay, we got to figure out how to turn it on even more before we start actually seeing reversal of aging. Like, we can slow down aging a little bit right now, but to actually reverse aging, we have to figure out a way to turn it on a lot.